from this.
Turn off.
You're not echoing. Perfect.
Okay, good.
Right.
We're now good. Okay, thank you, Kelsey. Yeah, so this is part of a series of meetings that goes back to the founding of ICAM in Santa Fe, New Mexico in 1999. And ICAM was formed at that time and has been going for the last 25 years with the vision of discovering the principles of emergence in complex, soft, biological, and quantum matter. Back in those days, quantum matter was called hard matter, but we've changed the terminology. And really, it is a venue for bringing together the full panorama of physicists who don't normally meet together with this unifying notion of emergence. And one of the notions is that by working together, by raising funds, philanthropic funds from national foundations, that we have the resources to help people travel and carry out research across this broad frontier. So I wanted also to welcome Christina. She is our new co-director. This, in fact, is the first in-person ICAM annual meeting we've had since before the pandemic. The last in-person meeting was held in Taiwan in January 2019, sorry. And we haven't had an in-person meeting since then, so it's really wonderful to get together. And one of the recommendations of the meetings that took place in the meantime was to broaden our co-directorship. And so we're really very happy to welcome Christina into the ICAM organization. She's been really helping us out over the last year and a half. And the other thing I wanted to welcome were various new branches that have joined over this period, and I hope I haven't missed any out. These include UCSB here, but also Bristol, the McDermott Institute in New Zealand, Emory University, and in the process of joining at the moment are the S.N. Bose Institute in Kolkata and the Institute of Science Consortium in Bangalore, and various other institutes that are in the process of getting interested. Lastly, let me say a few words about the program. ICAM has been committed since its outset to discussion. Our meetings are not wooden conferences, but they are dynamical events in which people interact and discuss the science that's being presented. And as part of that, we operate what we call the Frauenfelder rules, which means at least 1/3 of the time of the talk is devoted to discussion. So, of course, we didn't mention that before the meeting. And so, Oliver, I hope you're ready to take a few slides out. But that's how we typically run it. And you could start with a conclusion, and maybe. So the meeting is organized around 5 days of discussion, and the first 2.5 days are the annual meeting of ICAM, and the second 2.5 days are what we traditionally have as a frontier research area that is part of the annual meeting, and this rotates from year to year. It can be in any one of our thrust areas, biological, soft, or quantum matter. This year, we're devoting it to quantum matter, and so the second half of the meeting is also co-funded by the ICAM ExcelNet grant in quantum materials. And that's really helped us bring lots of extra people here. We have a lot of panel discussions as part of the week. This is something we really enjoy doing. It's a chance for us to talk about science policy and to think about the things that can really help our fields. Although we're a small institution, we punch above our weight, and many of the ideas we come up with often influence other organizations to plan the way they go forward. And so we've got some discussions this week on a broad range of topics, ranging from AI, quantum information, and various aspects of emergence, and please come and participate in those. We will have a panel sitting up here, but the main thing is the discussion with the audience that takes place. These are a lot of fun, and I really urge you to come along to these meetings. We will also have business meetings of ICAM tomorrow morning, and to that, anyone who's come here from a branch that's a member of ICAM, please come and represent your branch as a member of the Science Steering Council. There are a number of really important issues we have to discuss. And later in the week, the Science Steering Committee of the ExcelNet will meet together to discuss aspects of trying to organize our global network of quantum materials. So I think that's all the main things. Rajiv and Christina, is anything I've forgotten? I think we'll take a 5-minute break to allow Olivier to take a few slides out and to set up. and let me just remind you all that we're in a really beautiful place. If you get the chance, do take a walk at low tide on the beach. It's really magnificent, and it's just around the corner from here. If you have any questions, ask them now. Otherwise, look forward to talking to you all and meeting you all this week. Thank you.
Here's I wanted to add that it's nice that one of our previous co-directors, Dan Cox, is here, so we can pick his brain, right?
That's right. In fact, there are two here who were actually at the founding meeting in Santa Fe in 1919. We don't actually remember which year
It was 1998.
It was 1998.
Yeah,
Okay.
the march on the site was when we actually got money from the UCOP.
Yes.
So it was December of 98 when we had the first meeting.
Okay. Literally 25 years ago. Yeah, amazing. And I guess just outside we have coffee and things during the breaks. So look, I'm going to hand it over to Mark, who's going to chair this morning's session.
Recording in progress. So welcome everybody. I guess this is a dynamical test of the adaptability of the speakers. As mentioned, we're going for 40 minutes plus 20, and questions are welcome also during the talk. So the idea is to learn and the environment. There are quite a few locals here, so if people want suggestions or things to do outside the meeting, we'd be, I'm sure, happy to oblige.
Yeah, you just need to adjust the. Oh, that's great.
Yeah, that will help to skip slides.
There are no colored soldiers.
That's fine. I will adapt.
Are you ready?
Yeah.
You get an extra.
I get an extra 2 minutes at the beginning. Yes.
You can put that on slide.
Okay.
Okay, so Olivier Dauchot from ESPCI, Paris, is the first speaker, and I think you can all read, so the title is there, so take it away.
Thank you very much. So thank you for the invitation. It's an honor to present here the first talk of this meeting. And so Christina asked me to talk about collective effects. I will concentrate on collective actuation, will define it, and describing how I try to describe biological systems from the point of view of model physical systems. And I do both experiments and theory about all this. So here is the list of my collaborators. So I will tell you about active matter. So I don't know how I think the audience is pretty broad. So let me just recap. By active matter, we consider matter the units of which, well, the big atoms of which are consuming energy to produce some work, typically motion. And so, of course, it all started with biological systems in 95, so 30 years ago. And the goal there was to really describe essentially the collective motions of large assemblies of animals, from fish, birds, herds of gnu, or epithelial cells. And so this was a typical slide that you would have seen in the introduction in 96, 97. So I dug it up from there, archaeology, and so that's the general field. So it all started with biological system, but It was soon classified by physicists in terms of phases and symmetries, as we like to do. And so we rapidly forget about animals very soon. And so I will talk about polar active matter. So what is meant by polar active matter means that the kind of elementary units we deal with, not only they perform some work, but they have some kind of anisotropy. They typically break the tail head symmetry. And so there is a front and a back for each of the units. So as you can see here, for this mosquito, this sheep, or even the cell that can polarize. And the second thing is that I will concentrate on what is called dry polar active matter, which means that the units, not only they dissipate energy, but they can also produce or lose momentum in the ground. So they move on a substrate. So from the point of view of physicists, we have already broken two major conservation laws, the energy one and the momentum one, where we will stay with the fixed number of particles. Although in cells, this cannot be true, but from what I will discuss, it will be the case. Okay, and then phases. Well, you will agree with me that this looks much like a gas. This crowd of sheep looks more like a droplet with even a more or less well-defined interface. And this is more like looking like a solid, at least on short enough times. So it started with these collective motions, but in the past 25 years, it happens that active matter has motivated a huge amount of work in physics and has been exemplified as one of the simplest out of equilibrium systems for studying statistical physics out of equilibrium. The reason being that since the energy is consumed at the scale of each individual, you don't really need to inject the energy from the boundaries. And so you already don't have to deal with how this energy that you inject from the boundaries is going down the scales to your elementary unit. So you avoid all the problem of the cascade from the large scale to the small scales. You already start with small scales that are out of equilibrium and you try to build up a large scale theory from there. So that's why I think it's really helped and moved a lot the field of out of equilibrium statistical physics, and a number of phenomena were specific to active matter were discovered. So one is that, for instance, mechanical pressure is not a state variable. It depends on the potential that defines the walls on which you measure the pressure. So well, that's bad news from the point of view of theory, but it's an interesting fact. There is a liquid gas phase separation that takes place in a purely repulsive system. Is that? No, it's not an earthquake. Okay. You never know, you know, when you come here. So that would have made the talk very short. But I will adapt. So there is a liquid gas phase separation that takes place in purely repulsive systems, which of course is impossible at equilibrium. And then there are these macroscopic flows, these collective motion that emerge in the absence of external gradient. That is somehow you have in some sense, zero viscosity flows. Okay, so that was in the past 20, 25 years. And then more recently started to get interested in the solid phase. And in the solid phase, what I will show you are two interesting phenomena. One is the physics of flowing crystal, and the other one is what I call collective actuation, which is the emergence of collective oscillations in overdamped linear elastic systems, which again is something that would of course not exist in a standard solid. Okay, so let's come back to this biological system to start with. So these are epithelial tissues, and if you look at them at low packing fraction and you track the motion of a few of the cells, well, they perform some kind of random motion, probably with some persistence, but nothing dramatic, and it looks indeed like a liquid. But if you look at them at larger packing fraction, then what you see is that actually the cell, they do move like a little bit stochastically, but it seems that they perform some form of oscillation around the reference configuration, which is what I consider as the hallmark of a solid, that there is really a reference configuration to which the elements are pinned. So that's the first observation. That's in epithelial tissues. Now these are bacteria. So here you have what is called bacterial turbulence, where plenty of bacteria are moving here like millions, and they all move around. Again, it's really like a fluid. And this has been the topic of many research. But here I show you another case, again denser. And here what you will see is that they put a tracer in the bath, and you can see that this tracer is actually performing an amazing periodic orbit. And this is on scale of many bacteria, actually. So that's quite a puzzling observation. And then even later, so that's again in bacteria, Here I will show you not a liquid and a solid, but two solid behavior. So on the left, something that is very reminiscent of what we just saw. So again, this is 1 million bacteria. It's on Zoom, so there is delay. Okay, so you should see here an oscillation. Let's try again. You do. Okay, you imagine that there is some kind of time lapse. Okay, and on the other side, you will see that it's more like make a global oscillating rotation. Okay, I will mimic the videos if they are too slow. I will really have to adapt a lot here.
But are these suspensions of bacteria?
No, they are. It's essentially a monolayer. As I said, all will be essentially 2D or quasi 2D on a substrate, and that's important. And here they are on top of that embedded in some kind of soft elastic matrix, which will be key for the following. Okay, yes, don't hesitate in interrupting me. I mean, again, I can watch the time there. And okay, so we would like to go towards model systems. That's really what I've been doing in all my career. And so the minimal ingredients we would like to consider are active units, here restricted to polar units, as I said, some kind of a solid phase that we will have to manage to build up, not necessarily ordered, and then some form of aligning interactions between the motion of these little objects, but not necessarily mutual alignment, as we will see. Okay, and then doing this, we will produce two kinds of behavior. First, flying or flowing crystals, and then collective actuation. Okay, so let's start with introducing the actors at play. So even if these are model systems, they are experimental systems. So the first ones are these walking grains. They were designed in 2005, something like this, to study collective motions. You have little metallic discs, and these discs, they have two legs. Let's use this animal vocabulary. They have two legs. One is a very rigid made of the same metal at the front, and one is some very hard rubber. So these are the drawings of this object. And then if you put this on the shaker and you vibrate perfectly vertically at a frequency of typically 100 Hertz and a very small amplitude, what will happen is that these little things, but because they are very anisotropic, they perform some motion that is persistent. So you produce a persistent random walk. And so this is my typical animal. So you see that I went away from biology. I just retained the fact that they have a body. Sheep cannot cross. They have a body and they have a broken tail head symmetry. And that's it. And let's see what they do. The second ones are those guys that you can buy on the internet. It's a little kind of a toothbrush with a little engine inside, like the kind of vibrator that there was in the old mobile phone, and a battery. And well, this is the kind of ad that you can find, and it illustrates what these things do. Well, they mimic bugs. Okay. So if you want to describe this little animal from the very basic, well, there is this energy source, the battery, the polar tail head asymmetry, and then you write down the Newton's equation. Here we are in the classical world, and there's no mystery, which means mass times acceleration is equal to sum of the forces. There is the active force, which is the propulsive force in the direction of the body. Then there will be some damping. Here I take it to linear order in the velocity for simplicity. And then there will be external forces. And of course, because we are living in 2D, but there is, of course, the orientation of the body that is an additional degree of freedom. So there is also an equation for the torque balance. And so there is no active torque because a priori this has been designed in such a way that it doesn't systematically turn to the right or systematically turn to the left. So there is nothing propelling them to rotate. There is some damping because from external forces, there could be some external torques. For example, if another one starts pushing on the head or on the tail or things like this. And then we add some noise. This noise is not thermal, it's mechanical noise. We could also add some in the translational equation, but actually this one is really subdominant. What matters is really this one, because if you reorient a little bit the orientation, you change a lot the motion. Okay, so if you do this, you think you're fine, and you are completely wrong. Let's do a very simple experiment where we will avoid to solve this equation. Instead of doing this, we will impose the translational motion and look at the orientation one. That's something quite simple to do. You put the little guy in a little annulus where it can reorient, and you drive the motion of the annulus in translation. And what you can see is that at each corner, the little guy rotates in the direction of the motion that you impose. Okay, so that is not possible given these equations because this equation is completely agnostic to the translational displacement. So something is missing. And what is missing is a torque. It's a torque because it's something that reorients the body. And so the simplest torque you can think of is something that acts on that rotates the orientation. And what we show by performing other experiments is that this torque is proportional to the velocity of the displacement. Okay.
Simple question.
Yes.
The left-hand side is a scalar, J omega dot, and the right-hand side is a vector. How do we connect those?
Okay, so that's because, okay, yes, good point. So here I should write n hat dot. And so that would then be a vector.
N hat, okay.
Yes, so that's the orientation, but very often I also write it, only the angle equation, and so that's a typo in some sense. So if I write here this, then here I should have something like a sinus, the angle between the velocity and the orientation. Yes, it's a mix of two conventions. Yes.
In the picture, it looks like your hand is actually motivating it to turn. I mean, what?
Well, no, it's not.
Looks like it. Convince me it's not.
No, I mean, well, okay, so we did experiments with the XY table. That here, this is just the, the hand wavy experiments to illustrate, but with an XY table, and then we measured
So
the
what you have
evolution
there
of the angle.
What you have there is a magnifying glass showing the bug? What is that, the round thing in your hand?
The round thing in my hand.
No, there's your hand. Looks like there's what is that round thing?
This?
Yes.
So this is just a kind of little arena to confine the little bug, the little thing.
It's a box, they're moving the box.
Okay.
It's a box. So imagine you can even do it, okay, you can make the experiments like this. Find a bug somewhere outside. I hope there's no inside. Take a little glass, put the glass on top, well, like this, and then drive the bug. Even with a real bug, it works actually. You will see that it reorients. The reason is that it's completely generic. The reason for this is very simple to understand. You take this, you take the simplest polar active unit you want to build, let's say a disk. So you have to break the tail head symmetry. And so that's how you design this orientation of your particle, whatever it is. And then you don't want it to move systematically to the right or to the left. So you pay a lot of attention to make it left-right symmetric with respect to this vector n. But then as soon as you impose a motion that is not parallel to n, collinear with n, what happens is that, of course, the particle is not left-right symmetric anymore with respect to v. And because the dissipation force is typically an integral of local friction on the legs or whatever that was breaking the head-tail symmetry, the distribution of these forces is not more symmetric with respect to v, and so this is inducing a torque on n. So this is completely generic, actually. And indeed, if you take the little guy, where is it? The little guy from the top, the one I introduced before, the little walking disc, you see at the back here, there is a black dot. This is the back of the little animal. This is the place where there was the rubber leg. And I'm going to shake it, and it will more or less move as it can in this 1D geometry, but also there is a lot of rotational noise, so you will see it will diffuse in orientation, and then I will push it from the left, and you will see that the black dot will systematically be at the back. So let's do that experiment. Okay, it's performing its kind of random persistent walk, and then I push, and you see that the black dot is typically always at the back. Now you can do this with any walker, it will always be the case. As a matter of fact, it's also the case for us. We will do the experiment later. I will bounce on you from the left, and you will see that you will rotate. Okay, so
So the confining walls of this thing that you put in, is it irrelevant?
it is quite irrelevant from what I describe here. There is very little friction with these walls, and so it's quite irrelevant, yes.
In your demonstration here, that looks like external drive in some sense.
Yes, indeed. So what I do is that I completely remove the first equation, I impose V, and I look the effect on the orientation. There's another way to be convinced of this. Okay. now I'm under-adapting. But it's really important. It's take an inclined plane and launch the little animal perpendicular to the slope. If this torque is absent, it will try to move this direction, and also the gravity will move this direction, so it will go down the slope like a very bad skier. In practice, when you do this experiment, it turns into the slope. because this motion drives it to follow the motion, and so it rotates towards the motion and goes into the slope. It's actually the best way to have the signature of this feature. Okay, so we should move ahead. So is it important? If you perform a simple calculation for a standard active particle where this torque is absent, I will call this torque self-alignment, and you put it in an harmonic potential, which is the only thing we can do in physics, then what happens is that the little particle will climb in the potential, will balance the restoring force of the potential with the active force, will sit there at some position in the potential, and then will diffuse in the azimuthal direction because of the noise. And so the density probability of the presence of this particle will be something like this, instead of the standard Gaussian centered on the center of the potential. Now, if you do this with this kind of guys in a parabola dish, so this is a very cheap experiment, $5 the guy, $30 the parabola dish, and then you do it with a very weak battery, what you do observe is indeed that after some transient, the little guy climbs into the potential and then sits at some altitude and then starts to diffuse in the azimuthal direction of the potential. Now, when the battery is running properly, it orbits. And this is not possible if there is not this torque. So you can do computation for this. These are measurements of the situation. This is this diffusion, angular diffusion at a given altitude. This is the orbiting state. And if you simulate the equation that I just introduced, you produce exactly these two dynamics. On top of that, it's a very simple system of equations. You can solve everything, and you have the phase diagram. And the phase diagram is very simple. It's controlled by the two times controlling the dynamics, the one controlling the velocity, the one controlling the orientation. And if there is no inertia, that is tau v equals 0, you have a simple transition from the orbiting to the climbing state. That is a continuous transition. And if the inertia is large, then eventually this transition becomes first order. But in practice, in all the experimental systems that I know, the inertia is in these dimensional numbers always much more than 1 around here. Okay. So let's now try to make a solid out of all these little things, because that was the goal of the talk, the initial goal. So how much time do I have? 10 minutes?
Sorry, you've used 15.
Okay.
About the noise term, can you tell me why, you said it's not, does it have a time scale autocorrelation time or?
We took it not uncorrelated in this case. Yes, it's just a wide
If I do
motion.
these experiments where I move them much slower, you can see that this all.
Sure, of course. But I mean, you can consider the time as being like somehow coarse grain on a certain scale, and then it becomes really uncorrelated. The correlations in the dynamics do not come from there. I mean, there is already enough in the fact that the equation on the angle induce persistence on the equation on the translation, and that dominates everything. Okay, so if you take a bunch of these little things and put them on this shaker, what you observe, these are experiments, is this kind of motion. That is the little things by colliding, although these are hard disk collisions, there's very, very little dissipation between the collision, they form little clusters and they move together in the same direction in these little clusters. So that's when we were studying collective motion. So now I start adapting my talk, so forget about this. You can simulate the equations in periodic boundary conditions, and you see that it's indeed a massive flocking of all the particles moving in the same direction. You can do even very large simulation, and you essentially reproduce all the features of the well-known transition to collective motion predicted in the so-called V-check model. So that's first point is that, okay, the self-alignment plus collision leads to effective aligning interactions between the particles. Now we want to make a solid out of this, and these are disks. So it's simple, just compactify. We all know about the transition to crystallization in 2D. It's a bit specific. You all know it here. So we will try to compact these things just by increasing the packing fraction. And when you do so, you observe something very different from the equilibrium transition to crystallization. What happens is that you form clusters which are almost close packed. And it really looks more like a phase coexistence between those clusters and a more dilute phase. And the size of these clusters increase, and you have all the signature of a percolation transition of the size of these clusters in 2 dimensions. And you get up with a state like this, where you have one percolated cluster and a lot of disordered regions. Now it looks first order, but that's only the structure. So you can compute the pair correlation function. It's super nice crystal, nothing to say about this. But then when you look at the dynamics, the mean square displacement, forget about the slopes, but there is no plateau. This is not frozen. So although it's structurally crystalline, the dynamics completely decouple, it's not frozen at all. Well, you may say, well, but this is the mean square displacement, and so maybe what happens is that all these guys do not move, they are frozen, these guys move, and then when you compute the mean square displacement, you just add zeros to the one that move, and so you see a super diffusive displacement, but it's just the fraction here that is moving. It's not the case, because if you compute the overlap of the structure with itself, or the dynamical structure factor for those who comes from liquid state theory, it always goes to zero, which means that everybody moves more than its diameter on a given time scale. And the time scales are not crazy. It's even not glassy at all. The reason is that when you look at the movie of what is above, what you see is that it's full of defects. Come on.
So if you
Let me try to launch the movie.
sorry, I have a question.
Oh, it's stuck. Yes.
So if you separately calculate the mean square displacement of the fluid phase, does it have a different
No.
slope?
No, for the reason that there is no fluid phase, which is what you can see here. You have this crystalline phase with defects that propagate ballistically everywhere and that relax the structure very, very fast. So you can actually not identify two phases at odds with what the static picture would tell you. Okay.
So sorry, where is the, so size 6 is truly long range order?
No, because it's permanently interrupted by the presences of these defects.
So why is it a crystal?
So no, it's more an exotic phase. Okay, we have experts here. Yeah. Okay, now this is packing fraction of 0.84, and there is still room before close packing, which is 0.991. So what's going on there? Experimentally, it's really hard to prepare something back there. So let's start with the simulations. I hope I convinced you that the simulations were reproducing quite faithfully the behavior of the systems. And we can start with the systems where it's close packing, minus epsilon. And all the guys are packed. Now this time it's a crystal. There's no defect. And then we run the simulation. And you can see that the little arrows, or you cannot see that the little arrows are randomly distributed at the beginning, and then they perform this multitude of collisions, and after some time you will see that the whole crystal will translate from right to left. The color just goes the initial position, and you can see that the red are going now through the periodic boundary condition to the other side, and so you get a flying crystal. So there it's really crystalline, but the alignment still takes place, although it's very, very crowded, and moves the crystal. So we are very, very far for the moment from what we were expecting. We want to describe, don't forget we want to describe these oscillations. And we have a solid, we have active particles, they produce mutual alignment. There is not yet any sign of collective oscillations, but I still have 10 minutes. Okay, so let's try to 15. Let's try to pack the guys, let's try to confine them. If we don't want the crystal to fly, we should attach the crystal to the lab. So we confine it in this arena here that match the symmetries of the crystal, so that's why it's an hexagon. And just for reference, this is what happens for the similar disk, but perfectly isotropic. And these are experiments. So I put them on the shaker, and I have perfectly isotropic disk. It's not Brownian particle, it's still an out of equilibrium system, but it mimics pretty well what takes place at equilibrium. So here, this is really close packing, nothing happens. They cannot even move, they touch. And then you remove a few grains, a few of these particles, and you produce geometric frustration, so you get these kinds of defects. And at first sight, there is not much difference between the two types of disk. But then when you remove more of this disk, at some point for these ones, you again reach a defect-free crystal, because the packing fraction is still very high. You have just removed actually exactly one layer of disk, and so you just have a more dilute crystal, but it's still a perfect crystal. And here you have this sea of defects that makes the life completely crazy. Now, don't forget there is still this mutual alignment. And so when you look at the dynamics what you see is something quite amazing, which is that you have these things that are locally close packed, but not only they are close packed, but they align in these clusters, and then they follow the boundaries of the confinement in this flow. So what is the respective role of the defects and the alignment for this motion? Again, we can move to simulation to answer this question. So here, these are really the experimental condition. After some kind of a long transient, the system slowly organizes, and then you can see these lines of failure that appears, progressively disorganization in these triangles, and then it starts rotating when they are aligned, and you see that the failure occurs along these diagonals of the lattice. And because we are in simulation, we can reduce the noise and we can go to even higher packing fraction. And then in the limit of very, very small noise, since there is no quantum fluctuation here, we observed something that is a perfect temporally periodic and spatially periodic crystal rotating. And if you think about it, this is solid body motion, also here, also here. These guys here, they are making a very long travel. These ones are very small ones, so there must be shear somewhere. And the shear cannot be in the solid body part. So the shear is exactly there on these lines with this pair of defects that accommodate for the proper amount of shear at each time. So I find this phase quite fascinating. And it does resist in large-scale simulations. Although here we have to put some noise, because otherwise the simulation is just impossible to run. But we essentially see the same thing with a core where probably the shear is too large that isolates itself from the rest of the system. Okay, so I have to move forward, but this is, I think, quite interesting, surprising, unexpected, but we have really a bona fide flowing crystalline, or if I want to be really rigorous, kind of smectic phase. But okay, let's keep going. That's for experts. Okay, so it's not really synchronous oscillations. So what is missing? What is missing is elasticity. This initial system is really hard disk. There is elasticity, of course, as in any solid, but it's much, much too fragile. It's super, super stiff, and it breaks instead of responding elastically on reasonable displacement or deformation. So let's try to build something where there is elasticity. As a matter of fact, there were simulations actually performed by Silke with Christina quite now a number of years ago, where simulating more or less the same equations, except the alignment here was linear in the angles. There are some differences that we are still discussing with Silke, but it's essentially the same thing for very soft harmonic spheres. And when this system is very compressed and jammed, what you can see is that you have this kind of collective displacement, but when you look at the dynamics, you can see that there are oscillations. So there was a sign that for a much softer system, this oscillation could emerge from the same kind of equation than the one I just described. So that's what we decided to do, is okay, let's take the solid state physics book solid, masses and springs, let's take active particles, let's put them together, and let's see what will happen. And there's likely that there is something that will happen because the little arrows are forces, active forces. They will induce some strain. The strain is a tensor. The tensor lives in the same space as this vector field. And so it's likely that it will reorient the vector field. And so from this coupling, something may happen. Okay. So here is the little guy. So it's again the same annulus, plastic annulus. And these plastic annulus are connected by springs, and we'll build up a network with this. The physics is as simple as you can want. First, there is the active force that will elongate or compress the springs. That defines a length, which is the elastic length. And then there is this reorientation that I showed you before. And we can show that this orientation actually takes place on a displacement, not on a time scale, but on a length scale. That is, if you do it twice faster, it will rotate twice faster, but on the same length. Okay, so we have two lengths, and so I bet the control parameter is the ratio of the two lengths. Let me skip this slide, although there were nice movies, but I prefer to skip it. Okay, now we take the little springs, we pin them, and when the control parameter is too low, when this self-aligning torque is too small, well, you see some kind of a disordered motion of the little guides. Although these are probably not standard phonons because the vibrations have an active sources. And now, when the springs are softer, you get a collective oscillation of the system. So it's really this elasticity. So now here, we can see that for sure, this is not only linear elasticity, there's even a spring there that bends, it's large deformation. So will we have to take all this into account to understand that? We hope not. So we do a simulation where we take the equations, we take the overdamped limit, we take harmonic approximation for the elastic force. So we make it as simple as possible. We write down now the equation for the displacement with the dynamical matrix, and what we get is exactly the same thing as in the experiment. So the movie was a bit interrupted. So it means it's really only the elasticity. So here everything is completely linear. So it's only this nonlinear coupling term that is responsible of everything. And that's what we will try to understand.
Sorry, so they're actually linked together, or they just bump into each other?
No, they are linked by springs.
Oh, they're linked by springs, okay, got it.
And they never bounce. The springs
All springs, got it.
are there. It's really, you know, again, mass and springs textbook solid, except that the masses are active.
The masses are active, right?
Yeah, exactly.
Okay.
Okay, so now how much time do I have?
I make it 9 minutes.
Oh, you are very kind. No, but I think it's nice also to discuss. So let's see what I will tell you. Okay, one important thing, you can, of course, because it's a crystal, you can decompose the dynamics of the vibrating modes of the crystal. And when you look at this, you see something interesting. So is that the dynamics condensates on a few pairs of modes. This is noiseless simulations, and these are the experiments. They come by pair, and essentially they belong to the same class of symmetry. So for this lattice, it's the two lowest energy modes. Okay, not much surprise. But you can change the lattice. You can play with as many lattices as you want in this experiment. And for example, for this Kagome lattice, well, now the modes that are selected are modes 4 and 5. It's not the lowest energy modes. So that tells us that in these systems, because of this nonlinearity that is responsible for the oscillation, there is a nonlinear selection mechanism that includes the geometry and the polarization shape of the modes. And that, I think, is also interesting. That would not be the case at equilibrium, of course, where you would just stack the energy modes. Okay, so that's one interesting fact. Now you can, of course, not only change the lattice, but you can also change the pinning condition. And so instead of pinning the boundary, you can pin the center. And when you pin the center, you find these dynamics. So you will have like this a bunch of dynamics, and I try to think about the time I have at the same time. You can also simulate these dynamics. And again, you get a condensation on two modes. This time, the rotational modes and the linear combination of the two translation-alike modes. But again, it's a condensation on two modes. So this is very strong. Okay. So this could be the conclusion, but I still have 5 minutes. You remember these movies, and now this is an experimental model system containing the same physics as the one that is in there. Okay, so we have simplified it to the death, but so if we have active particles coupled by active particles that take the momentum in the ground, because that's very important, coupled elastically, you cannot avoid this kind of dynamics as soon as you have elasticity coupling them. That's the message. Okay, and in there is elasticity, and you have active particles that are polar and that they take their momentum from the ground. So this is the deep mechanism at the root of this behavior. So in the remaining time, let me skip this. Because that's too much detail. This is interesting to notice is that you can then ask, okay, what about simulation in much larger system? And then what you find is something that you do find this collective actuation, but there is all a regime in the control parameter where there is a coexistence between the center where the collective actuation holds and the boundaries where it's frozen. This means that there is coexistence in the phase space of the two solutions, and then they're organized in space depending on the boundary conditions and on the pinning condition. Okay, let me skip this. One message about this transition, you have oscillations, or your education tells us of bifurcation, and it's not the case. It's an original bifurcation which is called a drift pitchfork. No, it's not a pitchfork. A drift transcritical bifurcation. The reason is the following. When you look at these equations, you see that as soon as this one is 0, then the displacement is proportional to the orientation, and so this one is also 0. So because of this, you have an infinite set of fixed points. The guy is pointing in one direction, but it could be all direction because of the rotational symmetry. So there is always, so all the fixed points are actually marginal. They have a 0 eigenvalue. And this 0 eigenvalue will remain always there, independently of the control parameter. And then when you go across the transition, what happens is that, so the displacement increases in size, but it's still only fixed point, all marginal, and this fixed point at each value of the control parameter represent a circle in the phase space, or at least something topologically equivalent to a circle. And then at the transition, what happens is that you start drifting around this circle at 0 frequency. And when you go further, the frequency increases. So it's not a Hopf bifurcation where you would have an intrinsic frequency and it's the amplitude that would grow with the square root of the distance from threshold. Here it's almost the opposite. It's the frequency that increases as the square root from the distance from the threshold, and the amplitude does not matter. And this behavior that takes place at the level of one particle is also what is underlying the full transition for the big system. The story is awfully complicated because when you take this many body problem, it happens that now you have an infinite set of fixed points, and they don't turn all unstable at the same value of the control parameter. So you get plenty of coexistence of fixed point periodic orbits in phase space, and you have to decipher all this to understand the full physics. Okay, let me skip this. What I can say is that analyzing all this, we could get why there was a selection of these two modes. They somehow optimize something in terms of the instability of the fixed points. Let me just send a message. Now, if you look at the nonlinear dynamics, you can project it on the modes. It becomes very simple. Here, this is just an harmonic oscillator that is driven by the activity. Very simple equation, and everything, all the physics is in there. And you see that you have this 4-rank order tensor that couples 4 modes. And this is the shape of this tensor. And here also you can see that to have this non-zero, the 2 modes that are involved by pair should be maximally orthogonal. And if you want this quantity to be large, they should also be maximally extended. So that's the physics of what is going on. Okay, let me skip this. Okay, boof, boof. If you want now to understand the coexistence that I was describing between the 2 states, the disordered one and the collective actuation one, well, it's better to go to large scale and to try to see if you can write down continuum equation for these problems. And so we did some kind of coarse graining. As usual, there is some level of approximation. M is somehow the magnetization, that is the coarse grain field of orientation of the little guy. U is the deformation field. And when you do this, now the elastic force becomes linear elasticity. Okay, it's not so nice equation to look at. But anyhow, when you do this, you can predict, at least from the homogeneous solution, the coexistence in phase space between the disordered m equals 0 and the ordered solution m equals 1, bifurcating at 0 frequency, that coexists in these regions. Note that this solution, they are not connecting. The frequency is connecting, but the magnetization is 0 on this line and is 1, so they're actually completely separated in phase space. So it's a highly first-order subcritical transition in somehow. Okay, now just to finish with the video, in this experiment on bacteria, they could do something quite nice, which is that, let's hope that the movie, okay, so the movie are too slow here. And so we will not see anything. So on this one, the thing is oscillating like this, and then they change some parameter in the system of this bacteria, and it switched spontaneously to the other oscillation that I showed you at the beginning. And because we understood the source of these 2 dynamics, we could cook up a toy system that produced essentially the same the same thing. So here, this thing is doing this translational oscillation, well, more or less. And then we gently change the stiffness of the springs by pulling on them. And by doing so, you will not see it, at some point, it switched to the other regime. Okay, so I should conclude here. In the past, so all this started with this inspiration from biology about collective motion in active matter. And in the past 30 years, this has led to a huge amount of model experimental system, numerical models, new striking and interesting phenomena, development of specific kinetic and field theories, and a rather good understanding of these phenomena. So more recently, again, driven from the biology by the fact that in tissues, the systems are very dense and are these oscillations, we have uncovered somehow a new collective thing that is this collective actuation. And I hope it will drive as much enthusiasm as the collective motion. And, but a lot remains to be done to fully understand the physics of active solids. And here I think that the tools of harder condensed matter physics are likely to become increasingly helpful because we have to deal with this group of symmetries of the structure, etc., etc. So here are some references. Thank you for your attention. And I'm open for discussions and questions.
Okay, thanks for
I hope I adapted well.
Yes, perfect. So, questions? Okay, yeah, I think you were first.
Yeah, so I'm fascinated by where you talked about the biofilm kind of fluctuating. But what I probably missed is like, what sets the time scale of that oscillation?
The distance from threshold. Because this bifurcation is a bifurcation where at the transition you start with a zero frequency, what sets your oscillation frequency is the distance from the threshold of the transition.
Right.
It's not intrinsic, exactly as opposite to Hopf, where you would have some quantity that would set it. Here, it's really the distance from threshold that sets the value.
So that is fascinating because like what I was thinking is like in many times when you think about biofilm, we talk about like how cells lose this motility. It gets embedded in a system and possibly it can cause expansion by just growing or pushing things around. So, but that happens in like orders of tens of minutes time scale. But the fluctuation here is happening order of seconds.
Yes.
So that is
okay, so there is still a time scale indeed. So it's the distance from threshold. Of course, there is a prefactor. The prefactor is the oscillating frequency of the modes on which the dynamics condensed.
right.
So that will be given essentially by the stiffness of the elastic medium, the square root of K over M.
I think Xiaoming plus then Kendra.
Yeah, I have a question about the two modes. By the way, it's really good talk. So in an equilibrium elastic solid, you know, all of the modes get the same energy KBT, right? So here, is there a principle that we can calculate the projection of the active energy to the modes?
No, no. The only thing we know is that if you have zero modes, then there is a principle. You can demonstrate that everything will flow in the zero modes. If you suppress these zero modes, here by pinning, for instance, you have no principle at all. And that's what makes the story really difficult. And I mean, there was some work by Woodhouse where he could show that there was some kind of condensation in some region of the spectrum, etc. And here it's even more critical in the sense that it condenses on pairs of modes that are really selected by their geometry. So, and this is related to the tensor that makes the coupling. So if this coupling change in shape, it could also change the modes on which it will go.
So it depends on the macroscopic detail of the activation.
How far, I don't know, but certainly it depends on this nonlinear feedback between the activity and the strain.
Yeah.
Okay, so I have a question. So you showed us that there's a mode where it goes collective mode, which goes back and forth from the plane. The other way is the whole thing rotates, and it depends on where you pin it.
Yes.
Now, can you pin both the center and the outside?
I didn't try. I didn't try.
Would that be interesting?
Yes.
Back there, I think you're next.
Yeah, I have a question about disorder.
Yeah, yes. Okay.
Yeah, you put disorder in the spring cluster.
Okay, so let me answer a bunch of questions which are about the perspectives. So the perspectives is, what is the fate of this for very large system size? Because we are influenced by the pinning. But if the pinning is at infinite distance, then what happens? That's something I don't have the answer. The role of the noise. Here the transition is in a microscopic parameter, so it's a zero noise transition somehow. But now in the experiment, it's robust to noise. But of course, we did simulation at high noise, you kill it. So there is a transition in noise. It's a 2D system with alignment, so what is this transition in noise is an open question. Then there is a role of disorder. The role of disorder is super important in active matter because active matter is prone to develop rather long-range correlations. And so even in scalar, simplest active Brownian particle active matter, it has been shown that disorder at the boundary or in the core will, for example, destroy this condensation transition from gas to liquids that I mentioned at the very beginning. So disorder is critical in active matter. And so here we could have disorder by introducing lacunes in the lattice. So I have a disordered lattice, or disorder in the strength of the springs, more like in the spirit of quench disorder in an Ising system or in an XY model.
Yeah, that's
So,
what I was gonna ask.
and
If you
yes,
have any idea?
I have
you
no
worked on the
idea.
mean field version of this,
Yes.
a la Kuramoto? Because it
So,
seems like that
yes.
would be the easiest.
So
thing.
there is, when the dynamics condensate on zero modes, when you don't pin, then you can project the problem on an equilibrium system for the XY in the mean field. But that's the only case where we can solve it exactly. But so yes, all these are open questions for the near future.
It seems like a great topic for further discussion. Piers?
Yeah, looking on a broad brushstroke, of course, energy conservation is one of those central notions of conventional StatMech. Is there any notion of how to generalize StatMech to incorporate the non-conservation or the input of energy into a more general framework?
We don't have that. So the tools that we use typically to address this kind of problem is to write down the Langevin equations that would describe it, go to the Fokker-Planck formalism and try to solve for the steady-state distribution without any clue of it. However, if you look at the equation that I wrote, the nonlinearity is in the angular equation, and the out of equilibrium physics is in the first one, where there is the active force. This helps us a lot when we start to do theory about this Fokker-Planck equation, because actually the angular dynamics is an equilibrium one. And so from this, we can look for distributions which factorize a mix of Boltzmann-like, exponential-like behavior of the distribution for the angle, cross something for the translational degrees of freedom, and we can make some progress. But there is no, generic rules or paths.
Nicolas?
Yeah, so very interesting. You showed some examples where the distortions in individual springs was enormous, right? And in particular, also the biological systems are typically actually somewhat soft, right? So there's likely to be some amount of plasticity also. So
Yes.
it's kind of a twist on the
Yes.
this other question. So what happens
Yes.
when you allow sort of plastic deformations in
So
particular?
that was
the
my
focus is
next
strong.
perspective. It's what about the mechanics of all these guys? Because here, these are all spontaneous fluctuations, but then you would say, okay, let's take this solid and let's shear it, or let's do something with it. What will be the response? This is
And what
typically
would be
what it was.
the plasticity?
And what will be the plasticity? So if we go beyond linear elasticity, non-linear elasticity, plasticity, failure, all these, yes, of course.
Can you build this in your sort of active? I mean, is it easy to build? It's kind
So
of hard.
to be non-linear elastic, we are already.
Yes.
To have plasticity, we have thought about it. There are some, instead of gluing the springs, we could attach the springs with weak magnets so that they could unplug, send that. But okay, it would be reversible. But at least, yes, we could try. I think the best thing would be to also think about another system where we could do that.
Yes, yeah. No.
So you showed that to get the local orbits, as you see in the swarms, you need elasticity in your system. So I'm wondering, where is the elasticity in swarms?
No, there may be some confusion. So these oscillations that I described, so in the bacterial bath or bacterial monolayer, there the elasticity comes from there are two sources. One is the elasticity of the bacteria themselves, or the tissues, or the cells of the tissues themselves, or the matrix in which the bacteria are embedded. Mm-hmm. That's where it comes from. And that's why here, it's 3D model system, the simulation with the soft harmonic particles, since then with Silk we have been working at it again, do the same kind of collective actuation, and there the elasticity comes really from the interaction. Somehow, When you are so dense, you can do the Hartree-Fock approximation. Everything is an harmonic potential for each particle, it's if as they were attached by springs.
Yeah.
That's all.
Christina?
So to follow up on this, as you probably know, there are also these experiments by Yilin Wu.
Yes, indeed.
That puts bacteria in a viscoelastic.
But that's the one I showed. That's the one I showed. That's the one I showed. Yeah, that's the one I showed. And we interact with
They
them.
also don't.
No, exactly. And that's the one
But
where
they
they also do this.
And you
And
can
maybe you can
also
explain, can you
understand
elaborate a bit?
Sorry?
So
Can you
these are
elaborate
good
a bit
bacteria
on
in a
this?
viscoelastic medium.
Yeah, so
It's
this-
only if there is enough.
back. There's plenty of time, it's 10
viscoelasticity
minutes.
that you get these.
These ones. These ones, yes, these ones, so it's were done by Yilin Wu, and indeed, so these are bacteria in this viscoelastic medium, we should
Right,
say.
and there's only if there is enough viscoelasticity that you actually
Exactly.
get this switching. Of
Exactly, you need this elasticity.
So
And actually, they have a model in that paper that came out 3 months after ours in the same journal, and we had discussed with them before. And the model is actually completely on the same vein of what I described here.
So I was also follow up on Xiaomi's question.
Yes.
I mean, when we looked at this model 10 years ago,
Yes.
or actually 10 years, whatever, we did this mode analysis. And I think, if I remember, you might remember better than I do, but I think one conclusion was that, of course, you don't have the zero modes because the system is confined.
Yes.
But the mode that is controlled by the system size does play a role.
That's a very
And
tricky.
you can kind of, I don't think the details of the confinement are so.
That's a
clear.
tricky question.
Okay.
That system was amorphous.
Yes, well, it was
It was,
polydispersed.
yes, polydispersed and hence amorphous. So the spectrum of the mode is not, as defined as in a crystal.
Yeah.
And I think that, so indeed, if you increase the system size, then of course there will be modes that will become lower and lower in energy, and so you should excite more and more those. And this is something related to this question, what happens if you put the confinement far and further away? And we don't have a clear answer about this yet. But so the role of being amorphous or crystalline on one hand, then the size, because you see, you can go to the thermodynamic limit in 2 ways, increasing the size of the system, the physical size, or increasing the density of the nodes in a given size. And that will not produce the same physics, actually. This we have started to look at. So these are not so easy questions to answer. It seems that the part of magic, as always, that works at equilibrium, where everything at the end is 2 Lamé coefficient, will not work here. But
Dan?
Yes, so it's beautiful work. One question is, on the biological side, is there any utility to this for biological organisms? I mean, it's beautiful physics. Is there any?
well, I would ask. We should ask the bacteria.
Yeah.
So the bacteria do so. So I mean, this question of utility, I think we'll have it on the round table. I mean, utility is not all. They cope with what physics allow them or force them to do. So if bacteria are moving in a viscoelastic medium and pushing strong enough, they have to cope with this oscillation. Maybe it's adversarial, I don't know. So, I mean, there could be some things that you observe, especially in experiments that are completely artificial, even for the bacteria, that is not utile or not good for them, or has not been selected by evolution.
Right, I guess that's the question, like, I mean, you can create these things in these beautiful artificial environments, and the question is there any context in which those might be relevant for bacteria?
So the question, more generally speaking, the question is, okay, what about all the other spontaneous oscillations that we see? I mean, this is not a new topic. Oscillation in biological systems are omnipresent.
Right.
Some are driven by chemical processes, etc., etc. Are there some of them that we overlooked that are driven by this mechanism? Is probably possible, because when something can happen, usually it happens.
Okay.
But
Any questions from students? Well, okay,
Go ahead,
David.
go
No.
Speaking of
biology.
we are all students.
I'm still a
aren't we?
student,
Yeah,
exactly, especially in
yeah.
biology. It's well known in bacteria, if you, I don't know if you feed them at all, I mean, food mechanism, if they're starved, they go into collective modes and form different structures.
Yes.
Is that related at all to anything
I
you do?
I don't think so, not here. Here there are well-shaped bacteria. I don't think it's related. But
The shape isn't it?
no, but I mean well-fed.
Well-fed.
Yeah, well-fed, in good shape.
No.
Yes.
Thanks for your talk, it's really interesting. I was wondering if you or anyone else has done anything like this for mold, and is it very different?
Like what?
For mold.
Mold.
Fungi.
You mold like.
Fungus.
Yeah.
Fungus.
Fungus.
Mold different or?
I don't know. I don't know. I really have no idea.
Any questions?
But yeah,
from-
that would be nice to look
We
at.
still have 5 minutes. Any questions from other students? I think, oh, yeah, can
You had a question?
Xiaomin, no? Oh, okay.
Priority.
Okay.
Sure, you showed, I mean, I guess the videos didn't play, but you had these bacterial, where the oscillations were, you know, on much larger than bacterial scales. But you made a point in the model that this is not a Hopf bifurcation, that the frequency actually just grows away from the transition. Is that something that's observed in experiments as you change maybe the extracellular?
So there's not,
medium?
you know, it's exactly like in collective motion. So somehow we were inspired by this oscillation. Then we made this model system. Now we have a beginning of a theory. And so probably, I hope what will happen is that now there will be a new bunch of experiments trying to explore the transition. In the case of collective motion, there were these herds of, these flocks of birds. And then there was this Vicek model 95. There was hydrodynamic theory proposed almost immediately. And the first experiment where collective motions were seen, but not at very large scales, are the walking grains, 2010. And then there was the colloidal runners of Denis Bartolo, where really we could tune all the control parameter. And that was 2011 or 12. So it takes time then to find a system where you can check that the prediction of this behavior is actually reproduced in some real experimental system. But yes, that's what I hope.
Other questions?
Yeah.
I think,
Well, let
okay,
the students go
Xiaomin, then.
first. Yeah, sure.
Okay.
Younger faculty.
Yeah, we will go in chronological order.
Yeah, just add a question about the utility. I think if it's not completely clear what is the utility in biology, if we think of this as an engineered metamaterial, you
Yes.
think of any utility to
Okay.
engineering.
So let's be honest, that was the initial motivation.
Okay.
The biological stuff came later. When I saw for the first time the oscillations, I knew the oscillation in the one I showed you in the tissue I had seen before, etc. But the one in the bacteria, as I said, the paper came out essentially at the same time. So this I met for the first time in an APS conference like a few months before. The initial motivation was that I was working quite a lot with people from Leiden and Amsterdam, Martin van Ecke, Corentin Coulet, about these metamaterials, where they draw these units and then they drive them at large scale to produce one function. And since I was working in active matter for a long time, I said, but shouldn't we drive locally? Active metamaterials would be much more clever and you would not be imposed by trying to shear at large scale or compress, etc. And so we started thinking with Corentin in Los Angeles, APS of that time, can we build a system that would be a metamaterial with a little engine inside? And that's how all the story started. And so somehow this is the first simple metamaterial, except that the elasticity is super trivial. And now the idea, initially the idea was to replace the springs by buckling things, etc., so that then we would have two states locally and all the metamaterial story. But it took us already some years to understand what was going on there. But that's also a perspective in another direction, which is to now try to put this in systems where the local mechanical function would be more complex than linear elasticity.
Yeah,
Yes,
very
indeed,
interesting.
indeed.
Okay, Piers, then Ken.
I wasn't quite clear about your phase diagrams. You mentioned there were first order transitions, but are there second order? And if there are, do you think at the critical point the description will be
So they are
Zapmecki?
they are terribly first order.
Or version?
Yes, very first order. And it seems it's the case for most transition in active matter. Transition to collective motion is first order. This transition here is first order and badly first order. It's not only that you have in the Landau spirit something where you have the third order term that would have the same sign as the first order term, and then you would saturate the fifth order term. Here, what happens is that the branch in mean field you are second order, but the branch that bifurcates continuously from your original state is unstable at the bifurcation. And so you have a hole there in parameter space where you don't have any homogeneous solution. And you jump to some non-linearly selected one. And for example, in the case of the collective motion, there are three infinite families of solutions there, and the selection mechanism is driven by the noise, and no one's really know what it is.
Okay, last question, then we can continue.
This is either a crazy or a trivial question. So I was thinking that can you consider a situation where the bug is actually a quantum bug?
Yes.
And then have people looked into this, or do you know what might be expected, or how?
Okay, let me answer to this question through a little loop. I told you that everything was in this coupling between the alignment, well, between the polarity or the orientation of the particle and its displacement. Okay, so of course what I did at some point was, okay, but this I can put in an equilibrium model. So let's write a Lagrangian for liquid of spin. So ferromagnetic spins in the liquid that can move. And then let's put a self-coupling between the QI dot and the SI. Then what happens? It's an equilibrium system. So you immediately realize that if you do this, then the momentum is not just QI dot, because when you will derive your Lagrangian, there will be this QI dot SI. So the momentum will be the QI dot plus somehow the SI, which means that the total momentum is now the velocity of the center of mass plus the magnetization. And you have interesting coupling and an amazingly interesting equilibrium physics setting in. That was surprising, made 3 papers. Now, at the end of the day, the thermodynamic limit, you cannot have collective motion because the cost in the kinetic energy is, of course, too large. But there is also a phase separations, and for example, you have an amazing state where you have droplets moving, but the total velocity of the center of mass is 0. Okay, so this is very analogous to spin-orbit coupling. It's not exactly the same symmetries as the spin-orbit coupling, but it is the essence of that physics. And so many times I had discussions with people from spin-orbit coupling and whether we could have a quantum analogous to that. But we never went further in really trying to design one.
Right.
But that would be amazing.
Yeah, thank you
It's
very
a good
much.
place where to end.
Time for coffee.